Welcome to the webinar on Toshiba consumer and industrial motor control drivers. My name is Sven Hegner and I'm working in product marketing for the consumer and industrial market. Throughout this presentation, I will use the abbreviation MCD when I refer to motor control drivers. I'm excited to give you a quick overview about what Toshiba has to offer in this area. First, let's have a look at some key facts that underline Toshiba's competence as a supplier of motor control ICs. We can offer a very wide lineup. At present, there are 180 MCD products in our portfolio. Several new products are already in development and more are planned to be developed in the near future. Therefore, you can expect our MCD lineup to grow even further over time. Toshiba has a long history of motor control solutions. We have over 40 years of experience designing motor control products. Recently, we have replaced one of our first MCD products after 40 years of production in order to enjoy the benefits of the latest process advancements. For example, RDS-on has been drastically reduced in the latest BiCD-MOS generations. Toshiba has shipped over 2 billion MCDs, underlining our position as a major MCD supplier. There are Toshiba original technologies which are only available in our products and provide benefits to the customers such as improved energy efficiency. Last but not least, we continuously enhance our BiCD and CDMOS processes. These processes are used to develop advanced products that are manufactured in our fully owned Toshiba factories. I'd like to give you an overview on the motor types that are supported by our MCDs and summarize the advantages and disadvantages of each motor type. There is no one-size-fits-all solution. Each application has different requirements. Based on the specific application requirements, the best motor type and MCD can be chosen. The first motor type is brushed DC motor. It is called brushed because the current is transferred via brushes through the commutator to the coils, as you can see in the picture on the left. The major benefits of a brushed DC motor is it's simple to control, which results in a low-cost solution. On the downside, the brushes generate audible and electrical noise. Furthermore, the mechanical rubbing of the brushes against the commutator wears out the brushes. This reduces the lifetime of the motor. To extend the lifetime, periodic maintenance and replacement of the brushes is required. Another drawback is the reduced energy efficiency. The second motor type is called brushless DC motor, or BLDC motor for short. It is called brushless as no brush and no commutator are used. Therefore, no mechanical contact is required. This has several benefits compared to a brushed DC motor, like a long lifetime, no maintenance and low noise. Furthermore, BLDC motors are well suited for applications requiring high speed and high energy efficiency. All the benefits come with a price. Therefore, the downside of BLDC motors is higher cost compared to brushed DC motors. This comes from the more complex control circuit and inverter stage, usage of rare earth magnets, and in many cases 1 to 3 Hall sensors. However, there are also sensorless BLDC solutions available. The third motor type is called stepper motor. As the name implies, it operates in many discrete steps. Therefore, it is well suited for applications that require accurate position control. Stepper systems have an open-loop control. This means that no feedback from the motor to the controller is required. Therefore, there is no need for a costly positioning sensor, which helps to achieve a low system cost. The disadvantage of a stepper motor is that it is not well suited for high rotation speeds. At high speeds, the synchronization between control pulses and the motor may be lost. This is called step loss. In addition to that, there is typically a certain velocity band in which resonance effects take place, which can also lead to step loss. Moving through this velocity band quickly is no issue, as resonance effects need some time to build up. Toshiba has a long history in developing BiCD and CDMOS process technologies. These processes are manufactured in our own fabrication facilities. At the end of last year, we released the fourth generation of our 130 nanometer process. The G4 is a major improvement compared to previous generations. Firstly, it offers an ultra-low RDS(on) for N-channel DMOS transistors. Since the losses in the driver stage are reduced, the motor voltage is higher and less heat is generated in the driver itself. Another benefit of the ultra-low RDS(on) resistance is that it contributes to a significant die size shrink. As you can see on the right-hand side, in one particular case, a die size shrink of 45% has been achieved compared to previous processes. This leads to lower cost, but also enables the usage of smaller packages. The first products based on the new G4 process were released at the end of last year. The next generation processes are already in the pipeline. The G5 process is targeted to be released around 2023. The structure of our MCD part numbers is very simple. Let's take the part number TB67S128FTG as an example. The first section, in this case TB67, is a code for the used silicon technology. In this case, the product is implemented in a 130 nanometer BiCD process. The character S stands for stepper motor driver and 128 is the product name. For simplicity, I will only use the driver type and number when referring to a product. In this case, S128. The last section, in this case FTG, is a code for the package. For example, the code FTG refers to a QFN package. Next, I'd like to start with the introduction of our solutions for stepper motor control. In particular, I'll explain our original technologies for this motor type. Then we'll have a look at some of our product highlights. The first Toshiba original technology is called Active Gain Control, or AGC for short. This technology matches the motor current to the torque load. If the torque load is higher than the torque generated by the stepper motor, step loss or even stall can occur. This is to be avoided at all costs. Therefore, in a conventional system, the maximum motor current is applied all the time to make sure that there's always enough margin between the torque load and the torque generated by the stepper motor. This is depicted by the dotted red line in the picture on the bottom left. The drawback of this approach is that there is a lot of excess energy that generates heat and puts unnecessary stress on the motor itself. The wasted energy is shown as a gray area in the same picture. AGC is a real-time torque margin management system. It reduces the motor current to a configurable level, but makes sure that there's always enough margin between the actual drive current and the required drive current. The gray line in the picture represents the required motor current, necessary to avoid step loss and stall. The solid red line represents the motor current in an AGC system. It closely follows the load profile, but always ensures a margin to cope with sudden changes in torque load. By this method, the motor current can be reduced by up to 48%. This not only leads to higher energy efficiency, but also lower temperature inside the chip and the motor. In the picture on the right-hand side, you can see that the usage of AGC reduced the chip temperature by 30 degrees Celsius. This results in less cooling effort and cost, but also helps to prolong the lifetime of the stepper motor itself. This animation shows the concept of AGC by comparing a conventional system with an AGC system. In the upper part, you can see an object with varying thickness that is squeezed between two wheels. In the diagram below, the required motor current is shown in cyan color. The motor current depends on the torque load that is applied to the motors driving the wheels. The thicker the object squeezed between the wheels, the higher the torque load. The required motor current is the same for the conventional and the AGC system. The difference between both systems is that the drive current in the conventional system is always capped at the maximum. In the AGC system, it varies based on the necessary motor current. The green area shows the reduced power consumption of an AGC system compared to a conventional one. Another Toshiba unique technology is called Advanced Dynamic Mixed Decay, or ADMD for short. In conventional mixed decay systems, the so-called fast decay time is fixed. It can either be short or long. Both cases have their advantages and disadvantages. If it is short, there's a low ripple on the motor current, but the motor current waveform is distorted. If the fast decay time is long, a nice pseudo-sine wave motor current waveform can be realized, but there is a high ripple on the motor current. ADMD combines the best of both worlds. It provides pseudo-sine wave motor current while keeping the ripple current low. By this, up to 30% higher rotation speeds can be achieved without step loss. The upper right picture shows a close-up of the motor drive current waveform in an ADMD system. It shows successful step control even at high rotation speeds. The picture below shows a conventional mixed decay system. At high rotation speeds, step loss can occur. ADMD also reduces noise and vibration. In combination with microstepping, ADMD can realize the ultra-silent operation desired for many applications, such as 3D printers. In systems using constant current for stepper motor control, the drive current needs to be measured. In a conventional system, this is done via external shunt resistors, one for each of the two channels. The drawback is that these resistors are bulky and expensive. Furthermore, the current measurement is typically inaccurate. This may also have negative effects on stable motor operation. Advanced Current Detection System, or short ACDS, solves this issue. The current measurement is done internally. Due to a trimming process during production, the maximum measurement error is only 6%. The measurement error in conventional systems is typically in the 2-digit percentage range. The picture in the bottom left shows how large these shunt resistors are. Both consume almost the same board space as the motor driver IC itself. Therefore, ACDS can lead to significant saving in board space and cost. The first product that I want to highlight is the TB67 S128 FTG, or just S128. S128 is a single-channel stepper motor driver that supports up to 50 volt and 5 ampere. It supports up to 128 microsteps in hardware and up to 1024 steps if the step control is done via SPI. The 1024 step mode requires an external entity, such as an MCU, to directly control individual steps. S128 features the full set of Toshiba unique technologies that we just covered: Active Gain Control AGC, Advanced Dynamic Mix Decay ADMD, and Advanced Current Detection System ACDS. In addition to the before-mentioned features, S128 also offers a very low RDS(on) of only 0.25 ohm for low side plus high side. The combination of all these features leads to a set of powerful benefits for the user. S128 offers stall prevention, reduced energy consumption and heat generation, ultra-silent operation, support for high rotation speeds, reduced BOM cost and footprint. S128 is suitable for a wide range of demanding applications. Some examples are office equipment, surveillance cameras, 3D printers, ATMs and cash machines, home appliances and CNC machines. This list is not conclusive. There are many other potential applications. The second MCD that I like to highlight is the TC78H670 FTG. It is an 18 volt 2 ampere single channel stepper motor driver. Similar to the S128, the H670 also features 128 microstepping in hardware and the Advanced Current Detection System ACDS. It also offers the option to increase the number of steps to 1024 if the step control is done on an external MCU and transferred via SPI. H670 is actually the first product that is manufactured in the brand new G4 process. Thanks to this, the package size is only 3 by 3 mm, 44% smaller compared to the previous generation. In addition to the small footprint, this MCD is also very cost efficient, making it ideally suitable for applications like electronic door locks. One of the market requirements is to provide a high drive current for relatively low voltage power supplies. H670 addresses this by offering up to 2 ampere motor current. Another feature which is very important for battery-driven applications, but which also becomes increasingly important for mains-powered applications, is the standby current. H670 offers an ultra-low standby current of only 0.1 microampere. H670 is also a very versatile MCD, which can be used in many different applications. Due to its small size and ultra-low standby current, it's ideally suited for battery-powered applications such as electronic door locks, digital still cameras, digital single-lens reflex cameras, fiscal printers, and picoprojectors. In addition to this, it is also suitable for mains-powered applications like 3D printers or in iris and autofocus control of surveillance cameras. The second product category are MCDs for brushless DC motors. Also in this category, I'd like to explain the Toshiba original technologies and highlight two of my favorite products. The first Toshiba unique technology is called Intelligent Phase Control. This technology minimizes the power consumption across the entire speed range. Therefore, it is particularly suited for applications in which the motor operates at various rotational speeds. The beauty of this technology is that it is independent of the motor choice and speed. The figure shows the current drawn from a power supply on the vertical axis. On the horizontal axis, the rotational speed range is shown. The less current is consumed at a certain rotational speed, the higher the energy efficiency of the system. In order to reduce the current consumption, designers optimize the so-called lead angle. In a conventional system with a fixed lead angle, this needs to be done manually for every rotational speed. The dark gray curve represents a system that has been optimized for low speeds. Therefore, the energy efficiency is good for low speeds, but the faster the motor turns, the less energy efficient the system gets. The light gray curve shows the opposite case. This system is optimized for high rotation speeds. At lower speeds, the energy efficiency decreases. The red curve represents a system based on the Toshiba Intelligent Phase Control feature. The current consumption is always optimal across the entire speed range. How is this done? Intelligent phase control technology determines the phase of the motor current and motor voltage. In order to minimize the motor current, both phases need to be aligned. This phase adjustment is done automatically inside the MCD hardware. If the speed changes, the phases between motor current and voltage shift. Therefore, the readjustment of the phases takes place continuously. As I mentioned before, in a conventional system, the optimal lead angle needs to be manually determined for every single speed that is used in the system. If there are multiple speeds to be optimized, then this can have a significant influence on the development effort, time, and cost. With intelligent phase control, the manual effort needs to be spent only once. For all other rotational speeds, the lead angle optimization is automatically done by the hardware. This can lead to a faster time to market. The second Toshiba original technology is closed-loop speed control. First of all, what is closed-loop speed control? To explain the difference between closed-loop and open-loop speed control, let's have a look at the animation on the left-hand side. The upper diagram shows the external torque load over time. The picture in the middle shows the rotational speed over time for an open-loop system. The picture in the bottom is the same for a closed-loop architecture. In the beginning, both systems behave the same. Let's assume that at a certain point in time, the torque load increases. This causes a drop in rotational speed in the open-loop system. However, in the closed-loop system, there's only a slight dip in rotational speed. The MCD compensates for the increased torque load and brings the speed back to the original set point. The same happens when the torque load decreases. The speed of the open-loop system increases, while the speed of the closed-loop system has a small spike and then goes back to normal. The most important difference between both approaches is that the speed of the open-loop system did not return to the correct rotation speed. The closed-loop system maintained a constant speed except for 2 short periods needed for compensation of the torque load change. On the right-hand side, there are 2 architectures shown. The upper one is a conventional closed-loop system. The MCD provides a speed feedback signal to an MCU. The MCU contains speed curve information and a software algorithm for speed control. This architecture has a number of drawbacks. First of all, an expansive MCU is required, which provides the necessary resources and performance to compensate for speed fluctuations in a reasonable time. Even then, the response times are typically longer compared to a built-in closed-loop system. Secondly, the necessary software for speed control needs to be developed. Furthermore, the number of pins needed between MCU and MCD is higher, which might be an issue if there is a connector in between. The bottom picture shows an architecture with built-in closed-loop speed control. Any fluctuation in speed is immediately compensated by the hardware algorithm. Due to this, response times are minimized and an almost constant speed can be maintained. This is essential in mission-critical applications, such as cooling fans for electrical vehicle charging stations or servers, in which a certain cooling performance needs to be maintained. As the control algorithm is implemented in hardware, no software development is required. There are only 3 wires between the system and the MCD: speed information, direction, and brake. They may be provided by a low-cost MCU or any other entity. BO27 is a pre-driver for 3-phase BLDC motors. Pre-driver means that it contains the controller and the gate driver. The power stage is external. The chip supports a maximum motor voltage of 18 volt. Sine wave drive allows silent operation and reduced vibrations. In order to keep the system cost down, only a single Hall sensor is required. However, it can also be operated with standard motors equipped with 3 Hall sensors. BO27 incorporates both advanced Toshiba technologies, intelligent phase control and closed-loop speed control. There's non-volatile memory integrated to program the speed control, which eliminates the need for an external MCU. The external power stage makes the chip ideal for platform solutions. Every end product based on this platform shares the same MCD. By selecting the most suitable MOSFETs, the power stage can be scaled to meet the requirements of each individual end product. This allows a very high system flexibility. BO27 is perfectly suited for 12-volt fan applications. In particular for mission-critical applications such as cooling of charging stations for electrical vehicles, PCs and servers. In addition to this, there are also fans used in various home appliances and industrial equipment. B009 is a pre-driver for sensorless 3-phase BLDC motors. It supports a wide voltage range. The lowest operating voltage is just 5.5 volt and the maximum voltage is 30 volt. This IC supports Toshiba's built-in closed-loop speed control feature. Thanks to the embedded non-volatile memory, uniform rotation speeds of up to tens of thousands of rotations per minute can be achieved without the need of an external MCU. The gate drive current is adjustable up to 200 mA. This allows driving of external N-channel power MOSFETs with high current drive capability. An integrated current monitor completes the feature set. It allows the system to make real-time adjustments without the need of an expensive external operational amplifier. B009 is suitable for various kinds of high-velocity impellers and fan applications. Some example applications include servers, blowers, small pumps, cordless and robot vacuum cleaners. The third motor type are brushed DC motors. In this section, I will introduce you to some very interesting MCDs for brushed DC motors. The first product for brushed DC motors is actually a product family. It consists of two devices, the TB67H450 and the H451. Both MCDs are single-channel brushed DC motor drivers. They can handle a maximum motor voltage of 50 volt and can drive up to 3.5 ampere. The difference between both parts is minor. Both ICs feature an overcurrent detection, which shuts off the power stage if the motor current reaches a certain threshold. In case of H450, the chip stays shut down until a power cycle or entering and leaving the standby mode. In contrast to that, H451 automatically recovers after a specified recovery time has passed. In all other features, both chips are completely the same. Having an ultra-low standby current is crucial for battery-driven applications in order to extend the battery lifetime. However, nowadays also mains-powered devices have strict standby power requirements to achieve. That's where the isolated integrated voltage regulator comes in. If the chip is in standby mode, it consumes only 1 microampere, which is considerably lower compared to competitor products. Furthermore, the standby mode is automatically entered once both input signals in 1 and in 2 are low. This eliminates the need for external control. Both chips offer a wide operating voltage range. Due to their ability to operate at motor voltages down to 4.5 volt, these MCDs are perfectly suited for USB-powered devices. Another benefit of these devices is that they use an industry-standard package and pinout. This enables multi-product sourcing strategies as there are devices with the same pinout and similar functionality available on the market. H450 and H451 can be used in various applications. Some examples include printers such as fiscal printers, electromechanical latches in charging plugs for electrical vehicles, robot vacuum cleaners, home appliances such as refrigerators or coffee machines, vending machines, and electronic door locks. In addition to this, these MCDs can be used in all kinds of USB-powered devices. The next product family comprises TC78H651, H651A, and H653 for low-voltage brushed DC motor applications. These products are able to operate from a minimum operating voltage as low as only 1.8 volt. In order to extend the battery lifetime as much as possible, this chip family focuses on ultra-low power consumption. The operating current consumption of the IC is only 0.6 mA in typical case. The built-in standby functionality allows to switch off the device completely, so that no current is consumed in a typical case. Despite the low supply voltage, the motor torque should be maximized. H651 can drive either two brush DC motors or one stepper motor with 1.6 ampere per channel. If higher drive currents are required, H651A can drive up to 2 ampere per channel. H653 offers a so-called large mode, which means that in the case of a single brush DC motor, H653 is able to combine both channels in order to provide up to 5 ampere. The feature set is completed by the ability to support PWM frequencies up to 500 kHz and fast output switching characteristics. This helps to enable high rotational speeds. This MCD family works with a minimum operating voltage of only 1.8 volt. Therefore, these MCDs are perfectly suited for mobile devices running on one 3.7 volt lithium-ion battery, such as compact printers or digital still cameras. Furthermore, these MCDs can be used for devices running on two 1.5 volt dry cells, like security tags for self-checkout shopping, toys, and electronic door locks. This MCD family is also suited for all kinds of devices that are powered by a 5 volt USB power supply. Toshiba offers various design support resources to help you to get your products to the market as quickly and smoothly as possible. First of all, there is reference information and documentation available. Currently, there are 9 different reference designs listed in the Toshiba Reference Design Center on our webpage. Within each reference design, there are individual versions for several MCD products. A reference design consists of a schematic, the bill of material, and PCB layout files. These reference designs can be used as a starting point or source of inspiration for your own board design. On our webpage, there are block diagrams for several applications, such as robot cleaner, cordless power tools, and so on. Toshiba products are recommended for each of the blue colored blocks. There's also an FAQ section on our website, which provides answers to common questions related to each motor type. Each MCD has its own product page. You can find datasheets, application notes, and environmental information on these pages. If you need support during your product development, you may contact your distribution partner or the Toshiba application support team located in Düsseldorf, Germany. for the south of Europe, there's also a field application engineer for motor control located in the Munich area. In addition to the previously mentioned information, sooner or later you will need some hardware. You can get IC samples from your distribution partner, or you can order them at any time online via our e-sampling system. Up to 20 samples can be conveniently ordered free of charge via the system. Currently, 41 part numbers are available. Newly introduced products will be available shortly after the product launch. As for the evaluation and development boards, Toshiba is collaborating with third-party board makers such as Marutsu, Seed, Micro-E and Polulu. Currently, there are over 80 boards available. More will be released in the coming months. Thank you very much for your interest in Toshiba motor control drivers for the industrial and consumer market. I hope that this information has been useful to you in order to better understand what Toshiba has to offer. We simultaneously covered a lot and only scratched the surface in this presentation. There are many more Toshiba products available, and even more are in the pipeline to be released in the months and years ahead. Check out our website and subscribe to our YouTube channel so that you don't miss out on any exciting new product releases. With that, thank you for your time, enjoy the rest of your day, and I hope to welcome you again next time. Bye.